today talk of the PhD student and faculty seminar series. Today, Luca will talk about decompilers, and I think their application to cybersecurity. Luca is a PhD student in computer science and a member of the computer cybersecurity laboratory. That's the name. And that's it. Enjoy the seminar.
Okay. Hi everybody. As already Francesco said, today I'm going to talk about decompilers. And before starting telling you what a decompiler is, I really prefer showing you this. And I really hope you can guess what this strange code is, which is assembly. And assembly is the lowest level of abstraction you have between your code and the processor. So basically, when you compile some code, you get something like this, which is translated to byte sequences, and then the processor knows how to execute our program. And how many of you can understand what does this program? I see that you are focusing on maybe this is a printf because it's written that it's a printf. And this push ABP, maybe this is the prelude of the start of a function, and this is a rect. Okay, it's not so clear. So this is my face every time I open a binary and see what is inside. And here comes the idea of a decompiler. So what is the thing? 2 words. I want to reverse the compilation process. So given a binary, I want to recreate the code that that compiled my code. Okay, sorry, I put it very, very badly. But basically, I want to read some C code, okay? Because assembly is really too hard to read. Or maybe if you know assembly, every program is open source, so okay. So she's just a brief of history. She's Cristina Cifuentes, and she put a milestone in the research of decompilers. And every papers that talk about the compilation cite her work, and so I thought it was important to give her a slide, because she created one of the first major decompilers named DCC, which is developed in 1994, and then the field of decompilation exploded in so many other applications. Why decompilers? So you have seen that the confused language is not as readable as C code. So yes, I want to understand what it does. Okay. Maybe you have a closed source software and you want to know what is inside, and maybe. And I repeat for the 5th time, assembly is not so good to be read. Then you realize you have a legacy software running on your server, and all the references be thrown in some bin, and you forget about it, and you do not know what that strange legacy software does. So they compile us again, and maybe you can try to find some bugs in the software, because you do not have the documentation anymore. But from my point of view, most importantly, is malware analysis, because nowadays there are so many malwares that do the evilest and stranger things you may think. And if I could read the code of a malware, then I can say, oh, it's trying to decrypt a piece of byte and translate to code, and then its code is a dropper which downloads another part of the malware from the web, and it's easy to understand that reading the C code. It's not so easy reading the assembly code. And I can improve dynamic and static analysis, because if I have the C code, I can put into each kind of static tools or dynamic tools which try the control flow graph and data flow graph and so on. So, given this very, very, very brief interlude to the compilers, let's see how it is made. There are a lot of things. Okay. it's like a compiler because all these steps are really similar to the steps of a compiler, but on the opposite. So the front end is the machine dependent part. So I take some processor, for example, the x86 specification or the ARM specification, and then I try to abstract it to an intermediate language. Then I have the universal decompiling machine, which is the part of the decompilers which try to infer some information about structure and types. And then I have the backend, which is language dependent, because I choose one of my favorite language, C, Python, and so on and so forth. And then I translate the graph that I produced using the UDM to Python. So, starting from the front end, we have the very first part is the disassembly. So I take binary and I try to recreate the assembly code. And it seems really easy. No, it's not, because the problem of this kind of code is like it has a dense instruction set. So if I miss one byte, I can easily detect a wrong instruction. This is a very clear example. So if you have 1058C3 is the add with carry of something, but if I forgot the 10, I have a pop EAX and a return, which is the end of which is quite similar to a return, an end of a function. So there are so many algorithms that try to treat the best disassembler, and it's not so easy. But I'm going to forget about this, and I'm going to assume that it is easy and it's done, because it's done. So we are happy, and the major tools that I'm going to present in the last slides already do that. So I want to abstract a bit more from the assembly, because, well, I want types, I want structure, I want loops. So the intermediate code generator simply translate to a language. Okay, there are too many languages which I can use to this part, and I only to mention a few: LLVM, BL, Easy, and that I do not know how to pronounce, are candidates for the translation from the assembly to the code. Why the standard decompilers nowadays choose language like LLVM or proprietary intermediate language? Only to mention, LLVM is very useful because there are a lot of tools implemented on LLVM. It has types, and it has so many useful properties, and well, there is a strong tool chain on it, so why not? But all the others intermediate language can be used. Depends on the result you want to observe. So even here, I just forget about this, and I'm only to give you a brief interlude on what can be done. Then, okay, I have an intermediate language. So in order to try to reconstruct the structure of my code, I translate the code to a graph. So every time, I basically pack a list of instructions into nodes, and each time I have a call or a jump, I just create another block, and so on and so forth. So I use two words, node and blocks. Basically, we are using the so-called basic blocks. Basic blocks are a list of instructions followed by a transferring instruction, which are jumps and call. Or a block is simply a list of non-transferring instructions, so for the other instructions, followed by another node. Imagine that you have a first cycle, at the end of the first cycle, you fall into another basic block. Okay? This is the case. Given this visual example of a control flow graph, so this is, I used a software called Cutter, which is embedded in a suite for binary analysis. But this is a a visual way to represent a control flow graph. Okay. So the first part is done. I have a graph, and I want to retrieve some more important properties of my code. Okay. So I have only generated an abstraction of the input binary. The first part is the data flow analyzer. So I try to simplify expressions. I propagate constants, for example, because if you think to an arithmetic operation, it's split in more and more a list of assembly instructions. So for example, a linear combination of variables have 4 or 5 instructions. Okay, maybe I can just list only one instruction. So this is what expression propagation does, and constant propagation. Then, due to the fact that I have propagated something, maybe there is something that is useful, that is not useful anymore. Maybe there are some variables that is not reached anymore by the program, so I can eliminate it. And this is the same for a condition. You can just think as a jump, which is taken from each flow of your program. So maybe there is no need for the jump. I have just to adjust the statements. And then here, I try to propagate the types. Imagine that your program calls a printf. Printf takes an input pointer to char. So that location maybe is a pointer to char. So I set this rule for my decompiler and then try to propagate this information and try to infer some much more complex type, such as struct. Then the control flow, because for and loops if switch are, I suppose, are very important. So I try to reduce I give the compiler some rules to simplify the structure of the graph. For example, if there is here a jump and there are 2 branches, maybe it's an if. There is a jump which go back to another node, maybe it's a for. So basically, this is the restructuring of a graph. Finally, I have a graph. So from the binary to the graph, I transformed the graph somehow, and now I want to recreate the C, Python, JavaScript, Java code, okay, whatever. So there is the code generator part, which is a function from graph to code, which for each instruction, I take the abstract syntax tree of the operation which is identified by that instruction, and then I translate it to code. It's simple. I perform some more optimizations, such as arithmetical expression simplification. So a plus minus a and so on, I can delete them, or just calculate some constants. So 10 plus another integer, I can pack them together. And then I perform further code structuring. So maybe my decompiler see that there is a loop, so there is a while true and then a break, and maybe this is a for cycle, okay? Why I have to read a while true. Okay, I really hope I didn't kill you with this part. So what's in practice? It's a bit confusing because there are still some freely available decompiler, open source decompiler. The first one is called Reddeck, is a decompiler developed by Avast, and I suppose you know which company is Avast. We have Snowman, but he's dead. He died 3 years ago, 2 years ago. I do not remember that's the date. And then, before commenting the X-Ray decompiler, I want to comment this one, because I read a lot of paper about Dream, about Phoenix, about how wonderful they are, how marvelous they compete against the commercially available X-Ray or Reddeck. No, Reddeck no, it's not the case. But they are not available, there is no open source code, so I just forget about them. Okay. And then there is the state-of-the-art decompiler, which is X-Ray IDA decompiler, which is $3,000 or $4,000 of license. Okay, so it's not for it's absolutely not free. There is the free version which does not work. So there is a huge gap between open source and closed source. Okay, and I really just want to, I'm going to close this presentation showing you the results of the compilation. So here you can read a very, very simple code. There is a very useful function which is just a sum of an int and a char which was cast to an int and free printf. Okay, it's easy. So on the left, you can see the result of Redec, which is the open source decompiler, and you can see that, well, it's really the same. Okay, it missed the cast, but who cares about the cast? No, sorry, I only take the main. I was joking, but basically it's really the same. And even IDA, the commercial and the very, very expensive decompiler, performs very well. Okay, it introduced two useless variables, but it's readable. Okay. So let's complicate a bit. I already told you about type reconstruction. So what about this? It's a struct with two integer field and a pointer to char. It's not so. It's not the struct of the life. It's simply something very useless. And I really want to see the results of those decompilers and see if they infer this type. Okay. So the code is simple enough because there is a for cycle. And then here, I just manipulate my struct. And this is the result. There, first of all, where is the struct? It's gone. There is no struct because basically how a struct is represented in memory. So in my stack, I just list there is one integer, another integer, and a pointer to char, which is an integer. Okay. So there is no difference. And here, in fact, it sees them like an integer because it's a pointer. Because to access the field of a struct in memory, I just need the base pointer and then the offset, like an array. So both of them do not understand this. And so type reconstruction is totally gone. Then, HIDA correctly reconstruct a first cycle while Redec see this awful while true break. So, okay, I know this is one of the how can I say? This is why IDA is so expensive and Redec is so open source. But I really, really hope that they're going to fill the gap. So, type reconstruction is a problem. But let's forget about this for one slide. And so you've seen why the compiler is useful because okay, the code is not perfect, but you can read it in C. And when you are reversing a binary, having a C code instead of a list of assembly instruction, maybe it's much more useful. I presented you the tools that have been developed and the one who died and the one who survived, and I gave you a brief overview of the results of the compilers. But more importantly, issues, type reconstruction, as you already seen, there is a very, very, very large gap in practice and theory because there is a lot of study here. There are a lot of papers that try to reconstruct type as well as they can, but it's very complicated. And much more complicated is readability. Readability for us is not for the machine. Machines are happy if they can reason with the registers and the locations, but we are not, because I really, it's a challenge understanding that this V5, sorry, it's a challenge understanding what this V5 stands for. Okay. So for machines it's very easy. For me it's not, and but maybe others can. And then compilation is a loss transformation. So basically I'm losing things. I'm losing information. I'm discards types. I'm discards comments. I'm discards the name of the variables. So readability again. I can't recover everything. So there are things that we can try to concentrate our efforts, but we cannot invent, or we invent some new fancy names for our variables, or maybe it's a bit hard. So future work on my research topics will be study type reconstruction, if it wasn't so clear. And another idea is that maybe we need an interactive decompiler. So maybe the decompiler doesn't have to do all the job. So I just see the code and, okay, maybe this is a complicated first cycle or is a rolled loop because the compiler optimized it. So I type this information to the machine and then I try to use this rule to perform some transformation and improve the result. Okay? Here you can find only some references I used to create these slides, and if you have any question, thank you.
Any questions?
Yes.
Everything, you use everything that you have presented, you must know that the source code was derived by C. If you have a source code from another language.
Okay. There are two branches. Java, C#, all the object-oriented code are very easy to decompile. There are so many tools that do that because even the bytecode has too many meta information that you can fully recover it back. Okay. This, in this case, in the case of the example I put in the slide, they are C or C++ code, and you can infer which code is by the binary, because when you analyze C++ code, C++, in order to use namespaces and overloading, he manipulates the name of the function. So if the decompiler is smart enough and he can retrieve the name from the binary, then you see different name patterns. For the C, you see printf. For the C++ code, you read a Z, 63, and a very, very long name. So
after all, compilation is a function that doesn't necessarily cover all possible programs that you can write in assembler. So I would have expected that in some steps you should also be able to say this assembly code does not correspond to something at a higher level of abstraction. Okay. Does that happen?
As far as I study, I know, I think not, because there are some, maybe the decompilation will create some error, or maybe some instruction that do not lead anywhere, but in the from an empirical, very, very empirical analysis from all the binaries I have used for reversing, which were or malware or code for challenges and hacking challenges, the decompilation was kind of successful, in the sense that you cannot run the code, but you can read it and have an have in mind an approximation of what it does. If the question was you can execute that code, maybe not, because maybe it inserts something that cannot be executed or recompiled.
You're saying that you produce code that if you try to compile it,
yes, this is another great open issue, because the focus of a decompiler is not the recompilation. It's just I want to understand what it does in a much more higher in a higher language. Okay, there are papers who try to fill this gap and try to reproduce a code which can be compiled again. For example, to create a cross-platform version of that program. Okay, but this is not the case. Okay, this software I presented you if you gave them an input, a complex input, the result is not compiled, is not recompilable.
One is a curiosity, the second you already answered basically,
Okay.
but I'm phrasing in a way I can understand it. For me, it's an uncharted territory. The first question is, probably the malware setting, you're not assessing the assembly, you're really looking at the machine.
Okay. Yeah, both
The
look
assembly
at,
is one-to-one, but I expect it's a messy assembly.
there are,
That's a bit,
okay,
it's not as nice as the one you showed. Right?
I covered some sand under the sofa because yes, you're totally right. There are so many anti-debugging and anti-disassembler techniques. So here is just an overview of what can be done and maybe what it could be helpful. But for just one word, obfuscation.
Right.
There is
In the future, people might actually want to
yes.
make sure that you cannot do the job, right?
Yes. For example, I don't know if you know the MOV obfuscator, which is an obfuscator which translates your program in only MOV instruction. There is a paper which they proved that a program with only move is Turing complete. So yes, here if you gave me a MOV obfuscated program, no, I cannot decompile it. So in order to I think there are two different problems. The problem of obfuscating malware and the problem of analyzing malware. Okay, there are settings in which you cannot obfuscate malware. Think about this IoT explosion. You have firmware and you have a little space in your electronic device. So when you obfuscate a code, of course, it's bloating. Or okay, so in that case, this is useful. In the other case, you are, how can I say that? It's
The question you probably already answered
okay.
to Eugenio, but I want to ask you anyway. So when you were saying that you have two different translations,
Yes.
are they different in the sense that they're telling two different messages, or they are different way of translating the same thing? So they're actually doing, they're consistent with the assembly, or they're doing something different?
So you are seeing if they are semantically the same.
Yeah, it is
Okay.
nice to have, for example, one loop. This guy
Okay.
two loop and an if more than the second.
Semantic. Okay, so in the two decompilers I presented you, reconstruct semantically. Okay, but it is still an open issue. I read an article which I do not have put in on the slide because I wanted to tune some details, which tries to devise the perfect semantic of the input code, because instead of try to reconstruct the code from binary, he creates some Frankenstein code. So he puts code together, he compiles it, and then he sees if the compilation and the input program matches. Then he uses some genetic algorithm to improve the Frankenstein in order to match the input file. And this is semantically equivalent because they are the same bytes. And here maybe there could be something which is slightly semantically different, but on the purpose of readability, it's fine. Because if you notice here, and this is a very simple case.
I cannot read it from here, so
Oh, sorry. Okay. So sometimes, sorry, very often there are so many copy instructions that okay, you do not even know if it's semantically correct. Okay, that is why I put this fancy image here, because sometimes it's easier to read the assembly than the decompiler results. Okay? Depends on the domain.
You say that the result is usually not recompilable, but if this is the case, how do you assess the effectiveness of the decompiler? I mean, how can you be sure that the decompiler actually works? It cannot execute again and then compare the results with the
Okay. The problem is that okay, let me put it that way. You can see, sorry, you can read your assembly code, okay, and basically you're not trying to match, to have a one-on-one match. You are only trying to understand what it does. Okay?
Yeah.
Maybe there is some rubbish in the result, but you are not considering. Maybe you are just interested in understanding on the overall structure of the program. Right?
Yeah, but if I do this, it's because I trust the compiler.
Yes.
And how can I trust the compiler if how can I be sure the compiler works if I cannot recompile the result?
Basically, it's very more empirically. If the compiler is exploding with the copy statement, maybe there is something that is not working. Okay. If there are some, how can I say? The fact that you cannot trust the compiler result is strictly connected to readability, because when the compilers go crazy is when you cannot even read the compilation results. Okay, I understand this is a problem, because of course maybe the program was really that program. Okay, you're not sure, but in the term of readability, it's the same. So this can be answered with the paper I quoted 5 minutes ago. So I have a byte equivalence. In this case, no. I have not a reliable process to validate the results. But maybe it helps me understand what it does, that little piece, and then or the little piece of code, then do some manual refactoring only for understand what it does. Okay. But yes, you're absolutely right. It's an issue. Yes?
I guess, again, this is related to Eugenie's question about what cannot be decompiled. So, how about self-modifying machine? Did you try that?
And I've never thought about that. I'm going to try it, but I suppose, because I didn't try, and how can I say? As far as I know, you of course you do not catch the result of the self-writing, but you catch the instruction that writes. So the first part, the part that overwrite my statements, yes, I suppose, and I'm quite sure you can reconstruct and decompile it. But the others not, because it's a dynamic execution. This is only static analysis. Okay. Yes.
So it seems that it's more rather than producing some high-level code, you are really more interested in analyzing
Yes.
low-level code.
Yes.
So after all, in that case, you don't care very much to get something that can be compiled, but rather some warning that maybe some parts of the code are suspicious.
Yes.
So that might be a more useful thing than just producing C code.
Yes, but okay, understand the point. Okay, understood. And yes, I just want, or maybe it depends on what you want to do. From my point of view, it's just analyzing. So if I reduce the assembly to a nice abstraction, I'm fine. Maybe the LLVM abstraction is fine too, but I'm more I more see much better than LLVM, and I suppose so many analysts know C or C++ much more better than all the intermediate languages such as LLVM. So, but it's just it's not a scientific statement. So I don't know to explain. Maybe yes, maybe we can use less power than everything I presented you, but again, when you have C code or the graph, maybe it's the same. So maybe you can stop analyzing the graph. Okay, I think the C code is just it's fancy. Is the final result, and it's maybe more is a more readable result for someone. I don't know. Yes.
So what you're saying is that manual analysis is done manually.
Yes, because usually no, it's not so true. There are some automatic techniques such as signature analysis. So I have a large database of hashed binary. I have another binary. I take the signature of that binary and then I match it. So if I can understand if it's a malware or not if I have its signature in my database. So all the new malware, the zero-day malware, are not detected by signature base. Zero-day are a problem. Maybe if I could read the code, maybe I can detect a zero-day. Because okay, if I read the C code, there is a shell code, there is an execva, there is a gibberish of bytes ending with bin sh. Maybe it's trying to executing a shell, and maybe it's not a normal program. Okay, but maybe I don't know. I have maybe to analyze it better. Maybe I have to put it in a sandbox. But there are so many anti-debugging techniques, so it's not so simple. Something must be done by the analyst.